Hello to all space enthusiasts, romantics of the starry paths, and lovers of tough questions. I'm Dr. Max, your host for Celestial Chronicles. Today, we'll journey together through some of the most mysterious corners of the universe, from a binary system with an unusual mass ratio to an icy protoplanetary disk and a distant blazar. As always, space is ready to amaze, inspire, and occasionally baffle us. And I'm your guide through this world of stellar secrets and unexpected discoveries, the romantic and curious observational astronomer, Dr. Max. Get comfy, we're in for some brilliant revelations and a touch of cosmic philosophy. Let's go! The world of stars is vast and diverse, and it continues to exist beyond countless scientific classifications and categories. Take, for example, this binary system with the lowest known mass ratio in the universe. How does it exist right on the edge between total disintegration and merging? How does it manage to remain stable? Deep in the cosmos, two stars are locked in an extraordinary cosmic dance. Meet TYC 3801-1529-1, the most extreme contact binary ever discovered. Contact binaries are pairs of stars so close, their outer layers merge into a shared envelope. These fascinating systems, found in about 1 of every 500 stars in the Milky Way, offer incredible insights into stellar evolution. Scientists believe they form when two stars lose angular momentum and eventually merge into a single, rapidly spinning star. But here's the twist: there's a limit to how different their masses can be before the system becomes unstable. Enter TYC 3801-1529-1. First catalogued in 2020, it holds the record for the lowest mass ratio ever observed in a contact binary, just 0.0356. That means one star is nearly 30 times the mass of the other. This discovery not only shatters previous records, but also challenges long-held theoretical limits. To study this incredible system, astronomers used advanced techniques. They collected data from telescopes in Hoai and Xiang and analyzed archival observations from TESS and Super WASP surveys, spanning 16 years. They tracked changes in brightness, or light curves, and radial velocities to uncover its secrets. What did they find? TYC 3801-1529-1 orbits every 0.3659 days, less than 9 hours. The stars are transferring mass at a rate of about 56 trillion tons per year. The system is also heating up, with the primary star reaching 6206 K, classifying it as an A-type W contact binary. Here's the challenge: the mass ratio and spin-to-orbital angular momentum ratio of TYC 3801-1529-1 exceed theoretical stability boundaries. Over time, the stars will drift farther apart and the mass difference will grow. This binary system is destined to meet Darwin instability, merging into a single, rapidly rotating star. TYC 3801-1529-1 offers a rare chance to rewrite what we know about contact binaries. By studying it, astronomers can refine models of stellar evolution and witness the cosmic drama of a merger in action. Cygni is a red giant on the asymptotic giant branch, a well-known Mira-type variable star with a 408-day period. You can find it along the long bar of the northern hemisphere's summer constellation Cygnus, the Swan. In its gas-dust envelope are density waves, amplified by the star's periodic pulsations, leading to intriguing matter dynamics. Inside this envelope, various molecules form, like hydrogen cyanide, silicon monoxide, and carbon monoxide. Even from 550 light-years away, the spectral lines of these remarkable molecules give us a solid picture of what's actually happening there. Meet Cygni, a Mira variable star and one of the most intriguing giants in our galaxy. It's shedding light, literally, on the mysteries of stellar evolution. For decades, astronomers have studied Cygni to understand how pulsations and shock waves shape the layers of gas and dust surrounding it. These shock waves, powered by the star's rhythmic pulsations, play a vital role in forming its stellar wind. Recently, the Millimetre telescope array gave us the sharpest view yet of Cygni's circumstellar envelope, the vast cloud of gas and molecules enveloping this dying star. NOEMA's observations revealed stunning details. For example, molecular emissions like HCN and CO showed significant variability between 2023 and 2024. This points to episodic mass ejections, likely caused by the interplay of shock waves and giant convective cells near the star's surface. In one remarkable discovery, scientists detected an intense outflow in the northwest region, where gas appears to have been pushed outward by a shock wave. This localized event likely happened decades ago and left a distinct imprint on the star's surroundings. But it's not just about motion. The chemical fingerprint of Cygni's envelope is rewriting the rules. Observed line intensities deviate from models, suggesting complex processes at work, like shocks altering molecular abundances and radiation exciting the gas in unexpected ways. These findings challenge existing models of stellar evolution. To unravel the full story, astronomers plan to continue monitoring Cygni, using even more sensitive instruments to explore its dynamic changes over time. Cygni is more than a star, it's a laboratory for studying the forces that shape the universe. Space is hot ice and cold flame, the most saturated emptiness and the most rarefied density, finite infinity and infinite finiteness. From the hot gas-dust envelopes of retired red giants, we now move to the cold protoplanetary disks of youthful stars that are just beginning to become themselves. Here, icy crystals are only starting to dream of becoming planets, and they grow. Imagine a cosmic nursery where planets are being born. Meet PDS 453, a fascinating protoplanetary disk that's shedding new light on the mysteries of planet formation. Located in the Scorpius-Centaurus region, this disk is highly inclined, almost edge-on at 80 degrees, giving us a rare view of its vertical structure. It's a perfect lab for studying how planets emerge from swirling gas and dust. PDS 453 stands out because of its icy grains. Observations reveal a distinctive 3.1 micrometers water ice absorption band, originating from ice-rich grains in its upper layers. These icy particles hold clues to how water, essential for life, gets incorporated into forming planets. Using advanced imaging and radiative transfer models, scientists found that the disk contains a mix of silicate and water ice grains, with ice making up 10 to 20% of the composition. This combination affects how light is scattered and absorbed, shaping what we observe. At the heart of PDS 453 is a sharp ring structure at 70 astronomical units, a defining feature that marks the transition in density and scale height. This region plays a critical role in planet formation, influencing where and how planets might emerge. By combining data from the Hubble Space Telescope and ground-based telescopes like VLT Sphere, researchers piece together this incredible view of PDS 453. Their models bring us closer to understanding the intricate dynamics of protoplanetary disks. PDS 453 isn't just a disk, it's a time machine, showing us the early stages of planet formation. With upcoming tools like ALMA and James Webb Space Telescope, we'll dive even deeper into its icy mysteries. If you think stars don't have heart problems, HD 212044 will prove you wrong. This star pulsates like it's pounding out a hard rock rhythm with its swollen veins. We don't know what triggered it, but the beat is fire. B stars are some of the most intriguing objects in the universe, rapidly spinning stars surrounded by glowing disks of gas. But what happens when a star like HD 212044 doesn't behave as expected? B stars like HD 212044 eject gas into their disks through pulsations. These disks produce emission lines like hydrogen alpha, which astronomers use to study their dynamics. However, something unusual is happening with HD 2044. Using data from NASA's TESS mission and the BEST database, scientists found a surprising inverse correlation. As the star gets brighter, its hydrogen alpha emission decreases, something we don't usually see in low-inclination B stars. Further analysis revealed pulsation frequencies grouped in two ranges, 1.0 to 1.4 cycles per day and 2.0 to 2.5 cycles per day. When these frequencies align, called frequency beatings, the star's brightness spikes, hinting at dynamic interactions between the star and its disk. These findings suggest that HD 2044's disk is being fed through complex processes, possibly involving mechanisms beyond standard non-radial pulsations. It's a cosmic puzzle waiting to be solved. HD 2044 is more than just a star. It's a key to understanding the interplay between pulsations, mass ejection, and disk dynamics in B stars. The cosmos hides its shady business in the darkest corners of space. Blink, and across the universe reaches a punishing hand from above. But don't worry, it's all so far away that even light blushes from its slowness in delivering cosmic mail across centuries and parsecs of emptiness. And then comes blazar PKS 090357, a cosmic extrovert with an unstoppable energy fountain. Imagine a cosmic powerhouse hiding in the shadow of a bright star. This is the story of PKS 090357, a mysterious blazar whose secrets are finally coming to light. For years, PKS 090357 was hard to study because it lies just 0.67 arcseconds away from a bright star. Its classification and distance were uncertain, with earlier studies estimating its redshift at Z equals 0.695. But was that correct? A team of astronomers used advanced spectroscopy with SALT and the VLT to separate the blazar's light from the star. With exceptional precision, they uncovered a new picture of PKS 090357. Their observations revealed a redshift of Z equals 0.2621, much lower than previously thought. This makes PKS 090357 one of the nearest very high-energy blazars, changing how we interpret its power and emissions. But that's not all. They discovered a broad H emission line, with a velocity offset of 1,500 kilometers per second from the narrow lines. This is the first time such an offset has been seen in a blazar. This offset might point to a unique accretion state, emerging black hole system, or even a recoiling black hole launched by gravitational waves. Each scenario offers exciting possibilities for understanding active galactic nuclear. PKS 090357 is more than just a blazar, it's a window into the most extreme processes in the universe. With further observations, we're sure to uncover even more secrets. Everything in this universe is connected, women are beautiful, men are confidently tidy, stars shine, protoplanetary disks freeze, binary systems struggle to balance their masses, and blazars erupt in all-wave fountains of radiation. It seems like everyone in space has their own problems, just on a larger scale. So if you ever feel out of place, remember, even stars behave strangely sometimes, but they still shine. I'm Dr. Max, signing off this episode of Celestial Chronicles. There's enough sky for everyone.